Leetcode problem called construct binary tree from preorder and postorder traversal. So we want to construct the binary tree, and based on the two preorder traversal array and the postorder traversal array. So we have the preorder traversal array like this and the postorder traversal array like this. So we want to be able to construct the binary tree based on those two arrays, right? So in this case, both arrays are positive values and they're all unique, distinct values, right? So we will not have duplicate values. So that's one thing. You can see we're guaranteed to have at least one node, right, in our tree, right? So you can see the pre.length is equal to post.length, and they're all less than or equal to 30 and bigger than or equal to 1, right? So how can we be able to solve this problem? So to solve this problem, what we can do is that we know that the preorder traversal is current node, right? We visit the current node and we visit the left subtree, then we visit the right subtree. And the postorder is that we visit the children nodes, right? The children subtrees, then we visit the current node. So we visit the left side first and then the right side. So this is basically our binary tree, right? This is our output. We have node 1, we have node 2, node 3, node 4, node 5, node 6, and node 7, right? So for preorder traversal, basically we visit the current node, then we traverse the left side, so we have node 2, and then we traverse the left side of this node, which is node 4, and then there is no more children for this node, so we backtrack to node 2, and then node 2 we visit the right side, so we have node 5, there's no more children, so we backtrack to node 2, and then we backtrack to node 1, because node 2 we traverse all the children, and then node 1 has a right side, so we visit node 3, right? We have node 3 here, and then we traverse the left side, which is node 6, and then we traverse the right side, which is node 7, right? And basically, this is how we traverse using preorder traversal, right? And the postorder traversal, in this case, we're basically traversing the children first. So we have node 4, and then we visit node 5, right? We always start with the left side first. So once we traverse the children of node 2, we visit node 2, and then we traverse the right side, the right subtree, right? So we traverse the left side first, so node 6. So once we traverse node 6, we have node 7, and then we traverse the current node, which is node 3. So once we traverse the left subtree and the right subtree for node 1, for the root node, we visit the current node, right? Which is why we have node 1 here. So you can see this is the left subtree, this is the right subtree, and then this is the current node's value, right? So you can see that we basically, this is how we solve, or this is how we traverse the tree using postorder traversal. So there's a couple of ways we can be able to solve this problem. Well, one way we can be able to do is we can be able to do what we did in Leetcode 105 or 106, right? Where we can have a path, where we can have a range, right? So once we exceed the range, we can be able to continue to do our DFS, right? We can be able to backtrack if we exceed the limit. But the thing is that there's a better way we can solve this problem. Because if you look at this, this is the, for the postorder traversal, right? We can use the postorder traversal array to guide us where to search. In this case, you can see that for the children nodes, right? If the parent node is node 1, the children node's index will always be smaller than the current node's index, right? So in this case, node 1 has an index of 6, and their children's, right? In this case, node 2 has an index of 2. The node 3 has an index of index 5, which are all less than index 6, right? So you can see here that same thing for this subtree. Node 2 is right here, has an index of 2. And then the left subtree is 0. In this case, the left node is 0. The right node is 1, has an index of 1, right? So they're all smaller than the current index. However, though, if we know that there's a node that has an index that's bigger than the current parent, right? For example, node 6, that means, for example, node 6 has an index of 3. So therefore, node 6 is not a child node of node 2, right? Because in this case, the index is actually bigger. So what we can do is that we can be able to construct our binary tree using preorder traversal, to construct our binary tree. And we're using postorder traversal array, which is this one right here, to basically guide us how can we be able to construct our tree, right? To basically guide us how can we be able to construct our tree, right? So what we can do is that we're starting from index 0 in our preorder traversal. We know that this is the root, so we build our root. So we have node 1 here, right? So what's going to happen is I'll erase this. I'll start over. Basically, what's going to happen is we know that this is node 1, Okay, so we construct our binary tree. So in this case, what's going to happen is we're going to start on the next element, which is node 2. So node 2 in the post-order traversal has an index of 2, right? Which has an index that's less than node 1. So we know that node 2 is a child node of node 1. So we basically use preorder traversal, right? So we traverse the current node to the left side. And then we move on to the next element, which is node 4. So node 4, in this case, you can see, has an index, right, that is less than the parent node, right? In this case, the parent node has an index of 2, right? In this case, node 2 has an index 2. Node 4 has an index of 0. So in this case, the index, right, for node 4 is actually less than the index of node 2. So therefore, we're going to confirm that this node is actually the child node of node 2. So we build that, and then we continue. Then we have node 5. So node 5 in this case is not a child node of node 4, because node 5, the index is 1, and the child, and in this case node 4, right, which is the previous node, has an index of 0. So in this case, 0 is actually smaller than node 5's index, which is node 1. So therefore, node 5 is not a child node of node 4, right? Because like I said before, in the post-order traversal, the current node, the children is always come before the current node. So therefore, we can say that if I want to know if the current node is the child node of this node, right, the child node's index should always come before, should always be smaller than the current node's index, right? But in this case, it's not the case. So we backtrack to node 2, and then what's going to happen is that we know that node 2 has an index of 2, right? And node 5 has an index of 1. So therefore, we can be able to build that, right? We can say that node 5 is actually a child node of node 2. So we continue. We have node 3. Node 3 in this case is not a child node of node 5, because node 3 has an index of 5. Node 5 has an index of 1. So therefore, node 3 is not a child node of node 5. So we backtrack to node 2. Sorry, and in this case, we're comparing node 2, right? In this case, node 2 has an index of 2, and node 3 has an index of 5. So therefore, in this case, we have to backtrack to the root, which is node 1, right? So node 1 has has an index of 6, and then node 3 has an index of 5. So therefore, node 3 is a child node of node 1. So we build that here. Okay, so then we have node 6. So node 6 in this case has an index of 3, which is less than node 3's index, which is 5. So in this case, we know that we can say that node 6 is actually a child node of node 3. So we build that here, right? And then for node 7, in this case, the same thing. We know that node 7 has an index of 4. Node 6 has an index of 3. So in this case, node 7 is not a child node of node 6. So in this case, we backtrack to node 3. So node 3 has an index of 5, and node 7 has an index of 4. Node 3's index is actually bigger than node 7's index. Node 7's index. So therefore, we build it on the right side, right? So we have 7 right here, and then we basically backtrack to node 3, right? And then in this case, there is no more, because in this case, we finished traversing the entire array. So therefore, you can see the time complexity for this one is big O of n, where we're visiting each and every single node once. And its base complexity, because we're going to use a table, right? Because we're going to use, just like how we did it in Leetcode 106 and 105, we're going to use a table to construct the post-order traversal, so that if I want to access the index in the post-order traversal array, I can be able to use a table, right? So in this case, node 4 is index of 0, node 5 has an index of 1, node 2 has an index of 2, right? So we can be able to use a table to basically get or retrieve the index in the post-order traversal array in constant time. But that will also give us a space complexity of linear time complexity, right? So basically, this is what we're doing here, right? The code is very simple. But the core concept is that if the current index is less than the previous index, then we know that the current node is actually a child node of the previous node, right? If the current node's index is actually bigger than the previous node's index, then we know that the current node is not a child node of the previous node. So first, like I said again, we build the table. We have a hash table, and then we set the value as the key, and the index is the value. And then we do in our DFS. So in this case, our DFS, you can see that for our DFS, we basically pass in the previous index value, right? Previous index value, integer value, because we are trying to doing this, right? Like I mentioned. So in this case, we're starting from the root, right? You can see that we're starting from the root, and the root is at the last element in the array. So in this case, the only value that's bigger than the root, well, of course, we can do integer.max or anything. But in this case, we can just say that it's prev.length, right? So which basically is bigger than the root index, right? In this case, the length is 7, so that we ensure that this element's index is always smaller than the length of the array. So in this case, you can see here, we check to see if index is bigger than or equal to, right, the current index, right? This index is basically the pointer in the preorder traversal array. So we basically check to see, right, if current index is bigger than if it's bigger than, not this one, basically if we already iterate, or if we already visit all the nodes that we have in our array, right? If it is, we just return null. Then we retrieve the element that we're currently on, which is the current element, and as well as we get the current index, which is in the post-order traversal. So we check to see if pre-index, the previous index, is actually smaller than the current index. If this is happening, right, if this condition is satisfied, then what's going to happen is that, just like I mentioned, the current node is not a child node of the previous node. So therefore, we just return null, right? Otherwise, in this case, if this is happening, then we're just going to increase the index by 1. We build the current node, then we do in our DFS to build the left side and then the right side, and then at the end, we just return the current node value, right? So returning a tree node, and that's what we're returning back to this function, right? So basically, you can see this is how we solve the problem.